So here's my rotor assembly. And this is big, heavy iron core, DC, rotor's DC. It has, this particular one has cooling fans on it. It has bearings on it, so it spins nice and easy. Here's my 2 slip rings. This is where the 2 brushes connect. This guy, when hit with a DC current, produces a magnetic field. Higher the current, more magnetic field, more voltage is induced in the stator assembly. Rotor spins, it's got the pulley, it's got the belt, it's driven by the crankshaft. Okay, so this guy just has the 2 slip rings. It's got these big, heavy metal claw-shaped poles, and what this does is help concentrate the magnetic field. And the rotor is driven or rotated inside the alternator by the engine and the drive belt. I already said that. The rotor contains a field winding. It's one wire. How many ends on a wire? Well, there's 2. One goes to one slip ring, one goes to the other slip ring. It's just one wire, and it's all wrapped around here to increase its magnetic field, and then supporting batteries, blah, blah, blah. Anyways, so when this guy gets energized by the voltage regulator, so the DC amperage to run the magnetic field inside the alternator comes from the voltage regulator. Voltage regulator controls the magnetic field. Okay, so these finger poles, and it's 2 separate big pieces of metal that surround the rotor coil that helps concentrate the magnetic field into these spots right here, these open spots. You can actually see the rotor windings in the bottom. And much like the starter, these guys are just kind of, there's a very thin coating over them to get them close together so it can build a good magnetic field. And it swaps back and forth, north and south, and north and south, and north and south. Now, just like the starter, remember the starter, the armature was a laminated iron core, and it had cuts in it where the wires went through, and that helped concentrate the lines of force. So we got the finger poles in the rotor concentrating the lines of force, and that's concentrated into these gaps where the rotor, stator windings run through. Okay, so these windings are not connected to this laminate iron core. They just run through these little channels insulated in there. And if you look very closely, you can see how it's kind of run through and it's staggered. Like this one goes into this, groove right here. And then this one, you see how they're kind of staggered going around? Well, this is what gives us our different types of voltage, and we'll talk about that in just a second. So the rotor spins inside the stator. The alternating magnetic field in the spinning rotor induces the voltage into the stator windings. Rotor, DC, stator, AC. Rotor current is regulated by the voltage regulator. Low current side, maybe 10 amps of current, because we're using some energy from the spin of the rotor that boosts up the amperage coming out of the stator. Does that make sense? So what determines the output of the alternator? It's the speed of the rotor, how fast it spins, engine RPM, and the amount of voltage induced into the rotor, or put into the rotor by the voltage regulator, and that increases the output, the AC voltage in the stator assembly. So it's, how do we control the alternator? Vary the current going to the rotor and the speed, RPM, of the rotor. Higher RPM, more alternator output. Get it? So the stator is made of 3 windings. There's 3 separate wires in there. Each winding is placed in a different position compared to the others. They're staggered. And this laminate iron frame helps concentrate the magnetic field into the stator windings. The stator ends, these ends, right? This is where the stator goes. Wires, the 3 wires, the 3 windings inside the stator, go into the diode rectifier bridge. All right. three-phase windings. All right, so far we've been talking about, DC. DC voltages above the zero line. Well, we have alternating voltage, alternating current. It's alternating current is what comes out of the plug that you plug your lamp in your room, okay? Or your toaster, your microwave. That's AC. And all that means is we're used to DC. We've been talking a lot about DC. That's above the zero line, okay? Well, we can also have a negative voltage below the zero line. So it's the swing. AC voltage is the swing above and below the zero line. So these guys, the three windings, A, B, and C, swing as the rotor spins in there. They swing above and below the zero line. So if we look at A travels above and below this zero line right here, and then B travels above and below. And because they're staggered, they happen at different peaks. Get it? This is three-phase AC voltage. So stator design. Now, I don't want to spend too much time talking about this, but realize there's two different ways to do it. We got a Y wound, which it looks like a Y, but it's upside down. That's how they always draw it. I don't know why they don't draw it the right side up. And then we have delta, which is, like a triangle. So we have these three phases, and you can see like these two come together, right? See, these two come together right here. And then this one has a neutral junction. Y wound has a neutral junction. They do different things. And I'm just going to cover it really fast. Okay, so here's our diode pack. And then we look at this Y wounding and the delta windings. Oopsie, let's go back. The Y wounds, okay, goes to my diode rectifier bridge, okay? And as the rotor swings past these guys, say like this one is positive and this one is negative. This positive one goes, the diode, one-way check valve, allows it to flow out to the battery. But when this one switches to the negative side of the AC sine wave, it shunts that negative off to ground. It doesn't allow it to go to the positive of the battery. Then it does the same with this one, and just kind of ticks back and forth. Same thing with the delta. Okay, now they do have slightly different operations, and like a delta stator allows for higher current flow to be delivered at lower RPM. This is great for like police cars. Okay, anyways, so the diode rectifier bridge has several inputs and then really just one output on the B line. So and a ground, which is case ground. So we have these ground points, we have these, P terminal taps that come off of the stator winding, and then we have the big fat B lead. And this guy is what's in charge of changing the AC from the stator into DC to put out to the battery so we don't cook the battery. They go bad? Sure. The diodes start to go bad, we start either losing output or it starts to pass AC, whether or not the diode goes shorted or it goes open. Get it? If it goes shorted, it starts passing AC out to the battery, which will cook the shit out of the battery. Anyways. So we look at this, and as these leads on this Y wound flip back and forth, negative and positive, it shunts it off in the correct orientation. But like if this diode goes shorted right here, when this guy goes negative, it's going to be shorting out the battery. Get it? These one-way check valves are mounted in a heat sink because they get very hot. Anyways, yeah. So if we look at how this works, as the rotor spins past, this one becomes positive, which is allowed to go out to the battery, and this one is negative, which is shunted off to the ground. And then when it swings past this one becomes positive and is allowed to go out to the battery, and this one becomes negative and is shunted off to ground. Electronic voltage regulators. It's got a heat sink, dissipate some heat. We got the connections. We have the connections for the brushes. We have a B terminal, which is, collects alternator output and watches that as well into the regulator. All right, so look, here's how it works. We're driving along and we turn on the headlights. System voltage is going to drop a little bit. It's going to start digging into the battery. So the voltage regulator is going to kick up the current going to the rotor, and that's going to increase the voltage, system voltage, and put some voltage back into the battery. Get it? Now, say I turn the headlights off. Well, system voltage is going to go a little high because the alternator's been keeping up with this demand for the headlights being on. So it's going to see that. The voltage regulator is going to see that. It's going to drop the current going to the rotor. It's going to reduce the magnetic field. And then it's going to reduce alternator output so that the voltage remains stable. Get it? But the same thing happens if I speed up. Remember, rotor speed is taken into account as well. So I'm just cruising along and I speed up. Rotor speed's going to increase. System voltage is going to go a little higher. Voltage regulator is going to catch that. It's going to reduce rotor current to drop it down to a manageable level. What numbers are we talking about? Here's the important part. Write this down. Generally, charging system voltage, running voltage, runs 13.8 to about 14.2. Okay, that's normal charging system voltage. Now, there is some compensation on this. I just start the car. I just scrubbed a couple of 100 amps out of the alternator. It needs to be recharged. Alternator's going to whack it kind of heavy until, battery voltage comes up. And then it's going to drop back down. It's also got some temperature compensation in it. Cold weather. Cold batteries don't charge as easy. So it's going to whack it with a whole bunch of amperage, causing system voltage to be kind of high. It may go up to about 15 volts under cold weather. And this does two things. It helps recharge the battery and it helps warm the battery. So the batteries can warm up quicker. Get it? Okay, so there's this, the window we want to see is 13.8 to 14.2. But it can go a little higher than that for reasons. Now, it never goes above 15.5. You start seeing 15, 6, 15 and a half, 15.7, 16, 17 volts. You're done. Go home. And you've cooked the battery. Battery charging voltage needs to be held in a very tight little window. Now, if I put in like a AGM, AGMs have a smaller window. Okay? I mean, it needs to see, if it gets above 15 volts, that's a problem. Flooded lead acid battery, it can withstand that for a certain amount of time. There are specific charge rates for different types of batteries. So, these people throwing in an AGM in their car without having the charging system to back this up and to make it work well, probably going to be destroying those batteries rather quickly. Or, they go with these polymer batteries, which is new battery technology, especially on race cars. And, they're killing them. Anyways, so just realize that this output of the alternator varies according to RPM and load. And it takes literally a second for the alternator to raise or lower its output. So you can see this on a good meter, and we are going to look at this. I'm going to look at these numbers very closely. We good? All right, so the types of regulators. There's two basic types. Here's our field coil. We got a type A and a type B. Type A, the field coil has B plus on one side, so the regulator regulates a ground. Okay? And then we have a type B, which is the opposite. The regulator regulates B plus into the rotor. Remember, the rotor is just one wire. It's really not that hard. It's just a coil of wire. We hit it with a current, it becomes a magnet. Now, so regulator monitors battery voltage. The regulator controls the current flow through the rotor assembly. That's the spinny part. Voltage is induced into the stationary stator, AC. rotor DC, stator AC. Then coming out of the stator, we have AC. That's changed into DC by the diode rectifier bridge. And then that's put out to the battery. Have I said that enough? We good?